Alright, for this problem, we have some level ground, and we have some v naught at a given angle theta. And the question is, given the starting velocity and this angle, how high does it go, or how far does it go, or how long is it in the air, or sometimes all three? Of course, when this is starting, there's an x and a y component of velocity, and we know at this point basically that v naught y is equal to like v naught and then the sine component of theta, and of course the same for vox, v naught sine, cosine of theta. And that's pretty much it. From here, it's pretty easy to take care of the problem. As soon as we know that there's an x and a y component, we can take a couple other things and we can say, okay, well, in the y direction, the a and y is equal to whatever the gravitational constant is. As long as I'm going to ignore acceleration in the x, it's 0. And I ignore acceleration in the x because there's no air resistance, and there's nothing pushing against this ball. There's no force, there's no change in momentum, so this ball is just going to travel through the air naturally. So a of x is 0, a of y is g, and from there we can set up our problem. With that in mind, the key thing to know is that apogee happens halfway through the flight, both in terms of distance and in terms of time, because there's no air resistance. And at apogee, the key little fact is that the velocity in the y direction at that instant is 0. This whole time it started positive and it gets less positive, or smaller, until getting to the top where it becomes 0. It switches directions, and as it starts to fall, it becomes more and more negative. But right here at the top, the velocity in y is 0. While the whole time this thing is moving, the x velocity is constant. And these go off the page, of course. So solving the problem becomes pretty easy. The first step is find time of flight, which is the time to the apogee. And that's actually really straightforward. Velocity final equals velocity initial plus at. In this case, I'm going to look at the y dimension because the y dimension is the one that's changing. X isn't changing. At apogee, it's not moving, so it's got a final velocity of 0. Here is v naught y, or if you want v naught sine theta, your choice, plus a negative 9.8 times the time. Obviously, you're given v naught y, so the only thing you don't know at this point is time, so you solve for time. But that time is only how long it takes you to get to the apogee, which is only half the flight. So you take this time from this equation, and you multiply everything by 2. So you get like time to apogee. Oh, finger writing's hard. Time to, let's call it apogee AP, times 2. Okay, well that's good. But how about the horizontal range? Well, that's actually really easy because we have v naught x being, of course, v naught cosine theta, being equal to vx. These two things are the same because there's no acceleration. So this is just a distance equals rate times time question. This is just distance equals the v naught x times the time of flight you just found, whatever this is. That should take care of it. If you have any more questions, let me know.